Last time we were discussing the general idea of normalization, and as I pointed out, a very important part of relational database theory is the idea of normalization. The whole reason why we normalize is that at the end of the normalization step, you should have no data values duplicated in any rows. That is, more than 2 rows must not be identical. And also it is better not to duplicate the same data in more than one row. Every attribute in a row must have a value. That is, there shouldn't be any blanks for any attribute. And a deletion of a row must not lead to accidental loss of information. Like last time we saw that if you delete an order, the price of an item was lost in that process. And later on when you want to order that item, you don't know the price, and you have to get again the price from the vendor. Further, adding a row, that is updating the relation, should not affect other rows. In other words, whatever you add should be orthogonal to whatever already exists. A value of an attribute in a row can be changed independent of other rows. So, in other words, the attribute values, any particular arbitrary attribute value, if it is to be updated, you should be able to update it without disturbing the entire, that is, without having to search the entire relational database, you might say. Now, we look at the first normal form. First normal form is really nothing but converting an arbitrary kind of a format to a format which is really properly defined as a relation. That means every row has an n tuple, and it's a flat file. In other words, there is no particular attribute which has got multiple values, so that you don't get a variable record length. From the parlance of file design, all the records are of equal length. So you end up duplicating some of the rows to be able to get the first normal form relation. That is the beginning. In fact, it is not even normalized, you might say. It is just the zero state at which you start the normalization step. The first real normalization step is what is known as a second normal form, commonly written as 2NF. A relation is said to be in 2NF provided it is already in 1NF. In other words, we already said that normalization goes step after step after step. You start with the first normal form, go to the second normal form, go to the third normal form, then you go to the Boyce-Codd normal form, then fourth normal form, and fifth normal form, and so on. And each higher normal form is a refinement over an earlier form based on some difficulties people encountered in the normalization process. And so the normalization process, as I said, will always start with first normal form, then you go to second normal form. Before you go to third normal form, it should already be in second normal form. So in other words, second normal form is contained in the third normal form, you might say. And then when you go to the BCNF, then unless the relation is already in the third normal form, you don't go to the next higher step. So you go to higher and higher steps from lower and lower steps. So a relation is said to be in second normal form if it is already in first normal form. And no non-key attribute is functionally dependent on a key attribute. In other words, the problem which arose, we found when we deleted, was that the item code and price were related, and so when we removed an item from an order, the price was lost. So that means in this case, a non-key attribute, namely price per unit, was dependent on a key attribute. If key is composite, then non-key attribute can functionally dependent on one part of the key. Then no non-key attribute. In other words, if there is a composite attribute, the composite attribute together should determine the other attributes, and not a portion or part of the composite attribute. So let us go back to the example. We had order number, item code. It's a composite attribute, and we had order date, quantity, and price per unit, which is the original first normal form relation with which we started. Okay, and I look at a dependency diagram, and order number and item code is together, and as it's shown on this diagram, order date, quantity, and price per unit are shown as though it is fully dependent on the composite attribute, but it's not really so, because the price per unit depends on the if you look at this, the item code, the price per unit is dependent on item code, and so in fact this line should really be extended to that point. So in future I will extend that whenever there is a dependency of a non-key attribute to a part of a composite key attribute. Okay, the reason I showed it this way is that there is a tendency when you look at this to just put it like blindly like this, and which is in fact an error, because we know that from a word statement that price per unit is dependent on the item code. So it's not in second normal form, as non-key attribute dependent on part of the key attribute. Price per unit depends on item code. So you break up that first normal form relation into 3 second normal form relations. In other words, you go and through one single relation you break it up, so that this problem doesn't arise in that. So order number and order date is one relation which is completely self-contained. There is order date is dependent only on order number and nothing else. And prices, item code, price per unit. Price per unit depends only on the item code. And order details, for a given order, order number and item code together determine the quantity. Okay, and so you could actually put the order details as this. Okay, observe that a single NF is split into 3 2NF relations, which is in some sense you might say I seem to be actually making the result of the normalization more complex by putting more relations or adding more relations, but it's not really true. So because when I add these relations, I am really making sure that no problems arises when I update or when I delete or when I do certain operations like addition and so on. In other words, suppose a new item is going to be ordered which is not already ordered. In this case, I want to add an item code with its price in the prices list without really disturbing any others, because order is not there and order details, the order is not placed, so item will not appear here, and because order is not placed, it will also not appear here. Only this will be updated. I will put a new item code and put a new price. So updating is kind of independent. Suppose order number 1456 is cancelled, then I will cancel this, and this. Okay, these 3, and similarly this will be cancelled. Okay, that is, in other words, it will be deleted, and in that process I don't touch this one. Okay, because this one is not related to any given order. So the point I am trying to make is that there is a certain kind of independence between the updating as of this. For instance, suppose I change the date of the order, okay, but retain the item code, order number and quantity, then only the date can be changed on this without disturbing any of the other relations. So what has really happened is that deletion, additions, changes, for instance, if I want to change the price of an item 4627, like from 60.20 the price has gone to 62 rupees 20 paisa or something like that, then I just change this here and I don't touch any of these things. Okay. So similarly, as I said, if a date of order is changed, I only disturb this and I don't touch any of them here. Okay. So that is a great advantage of the normalization to second normal form. In other words, I am kind of making the relations, even though there are multiple relations, in such a way that any updation, any deletion or any addition does not cause unnecessary difficulty or ambiguities in the result. Okay. This is essentially what the whole idea is of normalization. Of course, there are certain operations like join, project and so on, which we are not going to talk about in this course, which will allow for certain kind of applications to be able to kind of combine more than one relation together. Like you may be able to combine these two for some purposes, but I am not concerned about it now. I am only looking at the question of normalization. So we have come to second normal form. Now the advantage of second normal form, which I of course already said, but let me just reiterate, non-key attributes are wholly dependent on the key. That is what we made sure. So repetition of order date is removed because it is a separate particular relation. If an order number for a particular item is cancelled, price per unit is not lost. And if in the previous case price was lost when a particular item was cancelled, the order was cancelled. And also I pointed out that if a price changes, I can just change that relation and not touch any of them. Duplication of data is not there, and it is kind of reduced. You might of course quibble and say there is some duplication in the sense that the order numbers seem to appear again and again, but then the reason is that otherwise, if I put this together, then this will become it won't become a flat file. In fact, it will not be in first normal form at all. Okay. So the reason this gets repeated because of the fact that I need to have essentially a flat file or relation where every attribute, every n tuple of equal size. There are 3 tuple, 3 tuple, 3 tuple in this case. So there are all 3 tuples, and that is the reason why I made sure that even though this looks like a repetition, but then you can see here there is no repetition here, there is no repetition here. Okay, and this repetition is kind of required repetition. So if there is a required, see, we don't start with second normal form. We said that second normal form has certain advantages which came about because of the fact that we did a normalization from first normal form. But this is not the end of the game, and the reason why there are higher normal forms, particularly a third normal form, you should understand very well, because in many situations in real practice, people do go up to the third normal form, and they may stop at the third normal form because it may not be necessary to go to higher normal forms. But I am not saying that you should stop there. It depends upon the problem. So, but third normal form is a very important part, because that is the one which from where I build on to higher normal forms. So third normal form, in order to get something to a third normal form, the relation should be already in the second normal form. And there is no functional dependency between some non-key attributes. See, in second normal form, we talked only about functional dependency between a part of the if you have a composite key, a non-key attribute being a function of a part of the key attribute. That's what we talked about in the second normal form. In this case, we are talking about the non-key attributes. So there should not be any dependence between some of the non-key attributes. If that happens, there is some little difficulty. So this needs further normalization if you find that there is a dependency, functional dependency, between some non-key attributes, because there will be unnecessary duplication data. Let me give an example of what I mean by unnecessary duplication of data, and what is meant by the functional dependency between non-key attributes. Take a relation student. I am giving the important parts of this, important attributes only. There may be many more attributes, but I am not concerned in the example with all the other attributes. So student, the key of course is roll number, okay, and name, department, year, and hostel name. Now, if all the students in say first year are put in hostel A, and all students in second year are put in hostel B, and all students in third year are put in hostel C, and so on, then it turns out that the hostel name and year are functionally related. That means if a student happens to be in second year, you know by implication that he will be in hostel number B. If he is in first year, you know he will be in hostel A. So year implies the hostel, and hostel names unnecessarily duplicated. Okay. If all students in the first year are changed to another hostel, many tuples need to change. Otherwise, we will decide that we built a new hostel, hostel D, where all incoming new students, maybe because enrollment went up, we put in that new hostel. Then you have to kind of go through the entire tuple set to change everywhere where first year and A hostel appears to first year and D hostel. Okay. So there is a lot of search and unnecessary work which goes on. So you change it into two relations, that is, you split up that single relation into two relations. One is student, roll number, name, department, and year. Now observe that the student relation has the non-key attributes are not functionally related, because the year of a student is not dependent on the department he is in. There are students of third year in computer science department, there are also students of third year in mechanical engineering department, and so on. So they are not actually functionally dependent, because obviously name is not functionally dependent on either department or year. In fact, there can be multiple Ramaswamis in a class, okay, and the unique identifier of course is only roll number. Okay. So you might say the name is related to roll number, but it is not related to any of the non-key attributes. So you make that first relation where all the non-key attributes are dependent only on the key attributes, and non-key attributes are not dependent on one another. And then you create another relation, hostel, where year becomes a key now and hostel name becomes the attribute. So if everybody in the first year is supposed to know what hostel A, it will be just 1 and A. So in other words, what will happen is that there will be, suppose there are in a college there are 4 years. This relation will have only 4 entries. If it is got a postgraduate also, then it may have 5 entries with a 5th hostel mentioned. I am making a basic assumption here that all students in a given year are put in one hostel. If in some situations students are all mixed up and the year of the student does not uniquely determine the hostel in which he stays, then of course this normalization step is not necessary, because the fact that year and hostel will not be functionally dependent, because it's arbitrary. Which hostel the person goes to, you have to only look at the entire relation, and because en masse students are not being shifted. Let me take another example. It's an employee relation. The employee code is the key for this relation, and there is a name, salary, project number, some project in which the employee is working. It's a company or something like that, where a number of projects, and each project is given a number, and a particular project will come to a termination date. Maybe when the project terminates, the employee will be shifted to some other project, or the project terminates, the employee also will be terminated. Depends upon the policy of the company. Whatever it is, if you look at the termination date of a project, it is functionally dependent on the project number, because any given project has a unique termination date. So non-key attributes, namely termination date, and a non-key attribute, namely project number, are actually related. So two non-key attributes are functionally dependent. So this is normalization. So you go to third normal form, where you put employee code, name, salary, and project number, and then separately you create a project relation where project number and termination date of the project is given. The advantage of this is, suppose the project termination date is changed, you only touch the project relation, you don't do anything to the employee relation, okay, and so that is the advantage. In other words, you can be somewhat independent it becomes, and suppose this primarily if the date is changed, if it is not normalized, then you have to go through the entire database, and every place that project number appears you have to change termination date. Whereas in this case you search through only one relation, you don't touch the other relation. Let me take another example. A passenger relation, ticket code. See, passenger buys a ticket, the ticket code, like a number which is given by our railways, called their PAN number or whatever, okay, and that ticket code, and that is a unique identifier of the ticket, and passenger name, train number, departure time, and fare. Now you can see that train number is related to departure time. So non-key attribute train number and departure time are related. So if suppose the departure time of a specified train is changed, then in this relation you have to go through all the tuples with train number and change all the places where the departure time is mentioned. Okay. So you now actually divided up into two parts: ticket number, passenger name, train number, and fare paid. Of course, it is not in a complete relation, because if you buy a ticket, you have an origin station, a destination station, and a fare. All that also is normally given. But for the sake of just illustration, I am not putting the full details of a ticket. I am just abstracting out some parts, some important parts. And of course, this was to illustrate the fact that a non-key attribute like train number and departure time, they are related. And so if departure time is changed, you have to only touch that. Okay. And so you got but for instance, similarly, if a passenger cancels his ticket, if there is only one passenger travelling by a particular train, it so happens from a particular origin station, then the information on departure time may be lost, because this is a pathological case. So I will not lose that kind of information. That is, when a passenger cancels his ticket, unnecessarily some required data may not be lost accidentally. That's what we showed could happen in a previous example. Okay, here also same thing. So if I put train number and departure time in a separate relation, so there is no possibility of losing that data. That is the advantage. Now, the third normal form is, as I said, reasonably good place where many people stop. But as I said, it is not the correct thing to do. In other words, you must look at further possibilities and further normalization steps which may become necessary, and among them the Boyce-Codd normal form, or BCNF, is the more important one. Okay, and assume that a relation has more than one possible key, and the keys are composite, and composite keys have a common attribute. This is an assumption. In other words, only in such cases you are required to do the normalization step of BCNF. In other words, a relation has a possibility of more than one possible key, and keys are composite, and composites have some common attribute. Give an example. I'll give an example. Non-key attributes not dependent on one another, of course, because already in 3NF. So non-key attributes are independent of one another. So the relation is in 3NF. Still, there could be problems due to unnecessary duplication and loss of data accidentally, even though it is in third normal form. Because of this difficulty, namely more than one possible key and key is composite. So take an example. So this again is an example with a composite key, professor code, department code, and the head of a department, and there is a percent time the particular professor spends in the department. Many universities have so-called joint appointments. There is a teacher teaches in more than one department, part-time in one department, part-time in some other department, and so on. This example assumes that such situation arises. Okay, so if I look at professor tuple, there is a professor code, and there is a department name, and head of the department, and person time. So if I put everything in one relation, I get this, and of course the non-key items, head of department and person time, are the non-key attributes. They are not related. So it is already in third normal form. So there is in this case there is a professor code department code is one composite key. It's also another composite key because every department has normally got only one honorary department. Normally departments don't have multiple heads for obvious reasons. There should be one person who heads the department. So the department and head of department are related. In other words, the head of department is it could be a key also. Okay, key, and so there are two possible composite keys. So BCNF arises only when this situation arises, namely you can take one of those non-key attributes and it's a candidate key attribute in a composite key. That's the terminology people use. It's a possible candidate for being a part of a composite key. Observe in this case that the head of department's name is repeated. Like Professor P1 teaches in physics 50% of the time, and Professor P2 teaches in physics for 75% of the time, and Ghosh is the head of the department, so Ghosh gets repeated. Similarly, P1, P2 and P1, P3 and P4 are in math department, and 50% there is a this Professor P1 is in for 50%, whereas Professor P3 is 100% and Professor P4 is only 30%, and he is 70% in physics. So Krishnan gets repeated in 3 places. See? So if Professor P2 resigns, that is, suppose Professor P2 resigns, then what do? You remove these 2 tuples from the database. That is, you delete this tuple and you delete this tuple. If you delete these 2, the fact that Rao was the department head of chemistry is lost, because Rao appears in only one place. He is not appearing in any other place. Okay, so P2 resigns. The fact that Rao is head of chemistry is lost, and lines 3 and 4 will be these two lines will be deleted, because when P2 resigns. So I lose information. So if I look at this dependency diagram, Professor code, department code. See, so head of department is functionally dependent on department. Similarly, a department is also functionally dependent on head department. Notice I could have put the head of department also as a possible composite key item. Okay, and so department head of department is really one dependency. Okay, so in other words, if I want to split, what I would try to do is that this fact is the one which I pay my attention to, and then try to kind of eliminate that. Okay. So I come up with a again we have seen that the given relation is in 3NF, as no non-key attributes they are independent of one another. However, there is a problem still pointed out. Problem due to the fact that there are 2 possible composite keys. An attribute of one of these composite keys depends on the attribute of another possible composite key. This leaves the problem indicated. Okay, and so identify the normalization to BCNF is based on identifying the dependent attributes in the possible composite key, remove them and create a new relation. So in this case, the composite keys are Professor code department and Professor code head of department. Okay, and so dependency is department and head of department. So new relations are, I put Professor code department percent time. Okay, head of department does not appear here. So even if some particular professor retires or resigns, the fact that a particular person is a head of department is not lost, because a separate relation here, which is department and head of department. So this is, whenever a department's head is changed, only this is changed and they will not touched at all. And whenever a professor changes his present time in a given department, only this relation is touched and this is not touched. So the whole point of BCNF is that you start with 3NF and you find out if there is a dependency, if there is a possibility that one of the non-key attributes could indeed be a part of a composite key. If it is so, it requires a normalization to BCNF, and you go to the BCNF normalization. So in this case, I am just taking the same relation, splitting it up into two parts. Observe that there is no redundancy, and if P2 resigns, increment head of department of chemistry is not lost. That is, the same person's name is not repeated in many places, and of course the fact that P1 appears twice is essential information, because he is spending 50% in physics and math, and P2 similarly has to appear twice, because they are unique, chemistry and physics. Okay, and P3 of course spending 100%, so it's only one line, whereas in this case there are two lines as far as Professor P4 is concerned. Okay, so the examples I am showing, of course, are you might say toy examples, small examples, but still we have to illustrate the kind of points I want to make. See, BCNF is okay, but one goes to higher normal forms in case there are multi-value dependencies. Okay, there is a, if I look at a fourth normal form, even when there are multi-value dependencies. In fact, both fourth and fifth normal forms are required only when you have multiple valued dependency, not otherwise. Okay, in this case I am taking an example of a project, a vendor and items. Vendor and items are multiple value dependency. In other words, many vendors can supply items for the same project, and also in other words, what I am saying is, a vendor is capable of supplying many items to many projects. Okay, and project needs many items, and project may order the same item from many vendors. Okay, so items may be supplied to many vendors, vendor is capable of supplying many items, and project of course may order the same item from many vendors, obviously. Okay, so multi-value dependency, if I take for instance vendor and project as a composite key, item is dependent on that. The vendor project item supply capability relation. This vendor is capable of supplying this item to this project. That's what it indicates. So if I look at the whole relation, V1, if I look at it as V1, P1, I1, V2, V1, P1, I2 and so on. That means vendor V1 can supply I1, I2 to project 1, can supply I1, I2 to project 3, and vendor 2 can supply I2 and I3 to project 1, and vendor 3 can supply I1 and I1 to project P1, and project P3 also can supply I1, the same item. So item I1 is duplicated for V1 and also for V3. Okay, V1 it is here and V3 also it is here. If V1 is to supply to project P2, the item is to be supplied is not decided. In other words, if suppose V1 is to supply to project P2. In this case, it is only supplying to P1 and P3. If you supply to P2, the item of the supply, what item is to be supplied is not decided, then there will be a blank here. The relations in BCNF, but still the above problem needs a further normalization. See, it is in BCNF because there is only one non-key attribute which can't be a key. Okay. The split the vendor item relation to two relations, resulting relation may have more than one independent multivariate dependency. In other words, must have not more than one independent multivariate dependency. So resulting relation is V1 I1, V1 I2, V1 V2 I3. Observe no unnecessary replication, and project P1 I1 I2 I3 are required. So this shows the project requirements. This shows the vendor capability requirements. So vendor capability is there. So suppose vendor 1 is capable of also supplying I3. It will appear here. V1 I3 will appear here, and it will not. There won't be any blank. Okay. Similarly, project P1 requires an item I4. Then I will put an I4 here, and it will not be a blank, because previously the project need not kind of have this requirement. So these 4NF stuff, I am not getting into great details because there is a lot of theory behind it, and you will learn about this in much greater detail in your course on database management systems. I am just giving a flavor of the normalization step, but the examples I am going to be illustrating with some case examples. Primarily we stop with 3NF or at the most BCNF. In 4NF relation, vendor capability to supply items and project need for items are there. They are applied by splitting the given relation. From vendor item relation, we said I1 is supplied to V1. That we saw that. See, we saw that project item. We see that project P2 requires item I1. P2 requires item I1. Okay. And vendor relation said I1 is supplied by V1. I1 is supplied by V1. Okay. That is quite clear. This would lead to infer that V1, P1, I1 must be a tuple in the original relation, but it is not really so. So this is vendor item supplied to vendor item relation. We say I1 is supplied to project P2. Okay. So P2, V1, P2, I1 is not here. V3, P2. V3, P2, I1 is only there. Okay. So it really means that the spurious tuple has occurred because vendor V1 may not be allowed to supply item I1 to project P2. That is not reflected in the relation. So another spurious tuple is V3, P3, I1, which we can infer. So V3, P3, P3 requires I1, B3 supplies I1. We may think that V3, P3, I1 is a relation which may not actually be there because he may not be allowed. So we need a third relation. This vendor project relation, that is, it shows that a vendor can give only citizen projects and not any project. So two 4NF relations together form the vendor project relation called 5NF relation. In other words, I got now three relations, and because the three attributes are all multi-value dependencies, I split up each one of the multi-value dependency into a separate relation. So effectively, if you go back to the original here, so I end up, because this multi-value dependency, I end up with a vendor item relation, project item relation, and vendor project relation. So that is the fifth normal form. So whenever you find such multiply valued dependency, then it is kind of time to split up. Then split them up into multiple you might say relations, and these relations are supposed to be in fifth normal form. And as I said, they are not occurring all the time in practice. It's people are kind of concerned. It's such multi-value dependencies and so on, and vendor capability and so on is not a very common occurrence. But anyhow, you should know these things. I mean, you should know before the full theory is detailed. I think you should know that these two exist. Okay. So I add one more and get the. Let me take some more examples of database design. The reason I am going to take some examples is to reiterate the things which I learnt and to apply our ideas to some examples. Okay. Order vendor item ordered example is we looked at a case study at the beginning of these lectures where a company orders items from a vendor, and the vendor supplies item to the company and it goes to inspection office and then purchase and so on. So we had a complete data flow diagram and we looked at the entire case study. So I am looking at a part of that case study and I am looking at the vendor order item relationship. In this case, order for items placed with many vendors. Okay, orders are placed with many vendors. A given order number is equals to only one vendor. Many items is applied against a given order. A given order may have many items applied. Vendor is capable of supplying many items, but only some items may be ordered. Okay. So vendors can supply many items, but I only can sometimes but he may be only certain items will be ordered from him. So general ER diagram is orders placed with vendors. So this is a relationship, and orders placed for items, and vendors supply items. Okay. So unnormalized relations are orders, order number, order date. So just by looking at this this diagram, I can just come up with a relation, unnormalized. That is a starting point. Orders, order number and order date. Order placed for order number item code, quantity ordered, delivery time allowed, and order placed with order number, vendor code, item code. And vendor code, vendor name, vendor address, and item code, item name, price per unit. Supplies, vendor code, item code, order number, quantity supplied, date of supply. Okay. Relations 1, 4 and 5, if you look at relation 1, it is a straightforward one. There is a key and there is a non-key, and this is functionally dependent on the non-key. 4 is also vendor code is, no composite key is here, see, single key is there, and non-key attributes are dependent only on the key attribute. So I have no problem. And similarly 5, item code is single attribute, single key, and item name and price per unit are dependent on the item code. Okay, so there is no problem. So in fact 1, 4 and 5 are already in third normal form, because of course here is only one non-key attribute, and item code and price per unit are related, whereas item name, there can be many item name is not a possible key at all. Okay, and these two are not really related, because this relationship is already there. Okay, there is only something which is not unique, so it can be a key also. Okay, so it is not functionally dependent. Okay. Relation 2 has a composite key. Okay, order number, item code is a composite key. Attributes of composite key are not related. Okay, So order number and item code, they are two independent orthogonal. Okay. No key attribute depend on composite, and there is no need for any change, because if I take a non-key attribute, quantity ordered, delivery time and time allowed, none of them is dependent on a part of the key attribute, and none of these are dependent on one another. Quantity ordered is not related to delivery time allowed. They are independent quantities. So there is no functional dependency here, and none of these is functionally dependent on part of the this. So there is no need for any it's already in 3NF. Order number and item code have multivariate dependency, but the order number relation to already has order number item code is composite key. So relation 3 can be reduced to order placed for order number vendor code. Okay, and because we look at this one, the item code, the 3 are not really necessary. Okay, and order number when item code is known, and if you know the vendor, vendor code, the item code appears right here. So you add that relation. Subplace, again there is a possibility problem here. There are 3, it has a composite key with 3 attributes. Item attribute and item code and order number have multivariate dependency. It has got many items can be supplied in one order. Needs normalization to 4NF. So normalized to 4NF. Actual supplies, order number, item code, quantity supply, date of supply, vendor capability. So I have split up the multiple value dependency into 2 separate new relation. So second relation is one more relation, vendor code, item code is there. So now my normalized relations are 1, 2, 4, 5, which have no problem, plus I add 7, 8 and 9. So I replace the old set by this new set. Okay. So this is the kind of steps you normally follow. Take another example. A student-teacher course example. A teacher may teach more than one course in a semester, and these are the assumptions I have made. Okay, and there is a dependence based on the assumptions. A teacher belongs to only one department. I am assuming that it is not a similar situation where a teacher has part-time in various departments. A teacher that belongs to only one department. A student may take many courses in a semester. A course may have many sections taught by different teachers. So, suppose there are 300 students in a class. Instead of one teacher giving to all 300 students, you may divide up the class into 10 sections of 30 students each, and 10 different teachers will be teaching the 10 sections. It's possible. Okay, I am assuming that a course may have several sections taught by several different teachers. So that means as a multivariate dependency. Teacher can teach many courses, and a course can be taught by many teachers. And similarly, students attend many courses. Okay, and student attends many courses, and courses may be attended by many students. Okay, obviously. Okay. So I will make the relation unnormalized to begin with. Teacher code, teacher name, address, rank and department. Now if you look at this relation, it's a fairly straightforward relation. The non-key attributes are not related to one another. Okay, because the teacher code determines the department in which he is in, because we said that a teacher belongs to only one department, not to multiple departments. Of course, name and address and rank depend upon the teacher code. the teacher courses got teacher code, course number, number of students, section, and course number, semester taught, course credits. These are two possible problems may arise here, but not here, because student number, student name, department year, there are non-key attributes are not dependent on one another, because department year independent, name and department are not related. So I think 1 and 4 can be kept as they are. And let's look at this 3. Well, look at the third one. Course number, semester taught, course name and credits. Well, there is no problem here, because course name and credits are not dependent on a partial part. See, so in other words, the course name is something which is not really a possible key at all. Okay, and credits of course is unique depending on the course. 1, 3 and 4 can be kept as they are. Relation 2 and 5 are multi-attribute keys which has multi-value dependency, but looks as though we don't need normalization. However, information on which teacher teaches a given student a specified course cannot be found from relation 1 to 5. So add a new relation, teacher student, teacher course, student number, course number. This set is normalized. In other words, now I can find out which teacher teaches a given student in a specified course, because I said a particular course can be taught by many teachers. So same student may take the same course from many teachers. So this is something which is not reflected in any of the previous relations, okay? Because I can't infer that from any of this 1, 3, 4 and 5. So I need a new relation, and I get now this set is now normalized, okay? So conclude, we have seen how data relevant applications are organized logically to several relations. The process of normalization depends on the semantics, meanings. So it is human intensive activity, it is not computer based, and one is normally satisfied with 3NF. There is a full-fledged mathematical theory which handles all this, which we will not talk about. So next time I will kind of look at DBMS, database management systems, and here I will stop this idea of normalization.